beneath the ocean floor, hidden from the world above, an engineering miracle is taking shape. Thousands of workers, billions of dollars, and machines the size of buildings, all swallowed by the earth. This is not science fiction. This is how humans drill tunnels beneath the sea. Today, we tear apart the entire process, layer by layer, rock by rock, machine by machine. From the first geological survey to the final concrete lining, nothing will be left unexplained. Before a single drill bit touches the ground, engineers must understand what lies beneath. Survey ships drag hydrophone arrays across the seabed, firing acoustic pulses deep into the seafloor. These acoustic pulses bounce off rock layers underground and return to the hydrophone sensors above. The hydrophone data is processed into 3D seismic maps, revealing faults, voids, and soft clay zones. Engineers then lower drill cores from the surface, extracting physical rock samples from hundreds of meters below. Each rock core is analyzed for compression strength, porosity, and permeability, the three properties that decide the tunneling method. Hard granite rock allows direct TBM boring. Soft saturated sediment requires ground freezing first. The heart of every submarine tunnel is the tunnel boring machine, the TBM. A full-size TBM can stretch over 100 meters long and weigh more than 3,000 tons. At the front is the cutter head, a massive rotating disc studded with tungsten carbide disc cutters. Each tungsten carbide disc cutter applies focused pressure to the rock face, fracturing it along natural stress lines. The cutter head rotates at 2 to 5 revolutions per minute, with hydraulic thrust cylinders pushing the entire machine forward with forces exceeding 100,000 kilonewtons. Behind the cutter head is the pressure bulkhead, a steel wall separating the pressurized excavation chamber from the rest of the machine. Inside the excavation chamber, pressurized bentonite slurry or pressurized earth is injected to counterbalance the water pressure from the surrounding seabed. Without this pressure balancing system, seawater would flood the excavation face in seconds. Excavated rock and slurry is pulled out through a sealed screw conveyor, the muck screw, rotating inside a pressurized tube. The muck screw precisely controls material outflow rate, maintaining constant pressure inside the excavation chamber. While the cutter head bores forward, the machine simultaneously builds the tunnel wall behind it. Precast concrete segments, each one weighing up to 8 tons, are fed into the TBM through the rear supply train. An electro-hydraulic segment erector grips each concrete segment and positions it precisely within the tunnel ring. 6 to 8 concrete segments are bolted together to form one complete tunnel ring, typically 1.5 to 2 meters wide. The joint between each tunnel ring is sealed with a compressed rubber gasket, the EPDM gasket, providing the primary waterproof barrier. Behind the completed tunnel ring, injection ports pump high-pressure grout into the annular void between the concrete ring and the surrounding soil. This grouting process fills all gaps instantly, preventing the surrounding ground from settling or collapsing inward. When the seabed geology is too soft, saturated sand, unstable silt, the ground must be treated before the TBM can enter. Ground freezing is one of the most powerful techniques. Liquid nitrogen or cold brine pipes are drilled into the ground from the surface. Liquid nitrogen at -196 degrees Celsius turns the surrounding pore water into solid ice, creating a temporary frozen soil wall. This frozen soil wall can withstand enormous hydrostatic pressure from the seawater above, providing a rigid, watertight excavation zone. Another method is jet grouting. High-pressure water and cement jets are fired horizontally into the soil, creating interlocking grout columns. These interlocking grout columns form a hardened matrix that transforms weak, flowing soil into a stable, drillable mass. Not all submarine tunnels are bored. Some are built using the immersed tube method, a completely different engineering approach. In this method, giant prefabricated concrete tube sections are cast in a dry dock on land, each section up to 200 meters long. Once cast and cured, the dry dock is flooded with seawater, and the massive tube sections float like ships. Tugboats tow each floating tube section out to sea, positioning it precisely above a pre-dredged trench on the seabed. Water is then pumped into ballast tanks inside the tube section, gradually increasing its weight until it sinks and settles into the trench below. Diverse and remotely operated vehicles guide the tube section with millimeter precision into the omega joint seal of the previously laid section. The omega joint seal, a massive rubber gasket, compresses under the hydrostatic water pressure, creating a permanently watertight connection. Inside a submarine tunnel under construction, the air quality is a critical survival parameter. Powerful axial flow fans push fresh air through rigid ventilation ducts running the entire tunnel length to the active excavation face. Carbon monoxide sensors, oxygen level monitors, and methane detectors are installed every 50 meters along the tunnel lining. Emergency refuge chambers, pressurized steel rooms stocked with oxygen and supplies, are positioned every 300 meters as blast-proof survival pods. When a TBM disc cutter wears out, which happens after cutting just 50 to 200 meters of hard rock, workers must enter the pressurized excavation chamber to replace it. These workers, called hyperbaric technicians, must breathe pressurized air mixtures and decompress in airlock chambers to avoid nitrogen narcosis. As the TBM advances, it must pass through multiple geological layers, each with different rock hardness, water pressure, and structural stability. In hard basalt or granite zones, the TBM cutter head disc cutters grind at maximum rotation, producing a grinding roar that shakes the entire machine. In soft clay or sand zones, the TBM slows dramatically. Operators increase the bentonite slurry pressure to prevent sudden ground collapse around the excavation face. When the TBM encounters an underground fault zone, a fracture line in the rock, engineers inject chemical grout ahead of the cutter head to stabilize the fractured rock mass. Laser guidance systems mounted inside the TBM track the machine's exact position and alignment, comparing it against the pre-programmed tunnel alignment model in real time. Deviation of even 20 millimeters from the planned tunnel alignment triggers an automatic correction. The TBM steering cylinders push harder on one side to curve the machine back on track. Now let's go deeper into the physics that makes submarine tunnel construction possible, starting with water pressure. At 30 meters below sea level, water exerts approximately 4 atmospheres of pressure on every square centimeter of the tunnel surface. This means the tunnel concrete lining must be engineered to resist both the crushing hydrostatic pressure from outside and the internal structural loads from traffic and soil above. Reinforced concrete segments are designed with circumferential reinforcement steel cages, curved steel rebar grids that distribute the compressive forces uniformly around the tunnel ring. The tunnel ring acts like a circular arch, one of the strongest geometric forms in structural engineering, converting external pressure into pure compressive force within the concrete itself. This is the same geometric principle used in Roman aqueduct arches, just scaled to industrial dimensions and inverted underwater. The grout behind the tunnel ring serves a second critical function. It transfers load from the tunnel ring into the surrounding rock or soil matrix. Without proper grouting, the tunnel ring would act as a pipe floating in loose soil, subject to ovalization, where external ground pressure deforms the circle into an oval. Once the TBM breaks through at the exit portal, the primary construction phase is complete, but the tunnel is far from finished. A secondary cast-in-place concrete lining is poured inside the segmental lining, adding another 300 to 500 millimeters of structural concrete thickness. A waterproof membrane, and typically a high-density polyethylene sheet, is installed between the primary segmental lining and the secondary concrete lining. Fire-resistant panels, drainage channels, electrical cable trays, lighting systems, and road pavement are then installed in systematic phases. Jet fan ventilation systems, powerful fans mounted in recesses in the tunnel crown, are installed to push air and smoke out in emergency fire scenarios. The final tunnel is not just a concrete tube, it is a life support machine buried under the sea. The Channel Tunnel connecting England and France stretches 50 kilometers.